Bless you.
Bless you.
Thank you.
Okay. Well, I'll give you some other information. This rod has length L, and it has a total charge of Q on it. Now, if I want to calculate the electric field out here from this little charge dq, it's going to make some little electric field in that direction right there, right? Radially away from dq right there, and that's going to be some little electric field dE, okay? And that's a vector. Now, one thing that's cool about electricity and magnetism is there's all kinds of good symmetry arguments. And one of the symmetry arguments that can be made is that for every dq up here, there's going to be some dq down here in the opposite direction like this, okay? That's going to have an equal but opposite component in the y direction. So we really only need to worry about the x component of dE. All right, but I'm getting ahead of myself. First, let's just talk about what dE, the magnitude of dE is. The magnitude of dE is going to be 1 over 4 pi epsilon naught times dq, that's our amount of charge, over r squared, right? This is just the electric field from a point charge as we had in the last, I showed it on the board a little while ago. Okay, but we have some problems here. We don't know how big r is, and we don't know what dq is, and we need to set this up and integrate all this stuff, okay? So we have a lot of stuff to figure out here. So this distance is r right here, and I'm going to set this up at the point we're talking about is some a distance away from this rod. Now, here's the important thing, is that this is the y-axis right here, this is the x-axis right here, and the distance to dq right here, that's y, right? It's being measured from y equals 0 up to dq. So if we set it up like that, r is going to be equal to the square root of y squared plus a squared. Okay? That's from the Pythagorean theorem. This is an important point at which you set r equal to something about the geometry of the problem. You need to do that. Okay. So far, so good. Now, something else is that I said that due to symmetry, we only need the x component, right? So here's something like this. I'm going to say this is an angle theta here. That means this is an angle theta here. So I need the x component. That's the adjacent component. So if I want to find dEx, that's going to be the x component of dE, and I'm going to add all those up. Well, in that case, I get 1 over 4 pi epsilon naught times dq over r squared. That's the magnitude of dE. But now I need the x component, which means I need to multiply this by cosine theta to get this little component of this vector. Okay, that means I need to come over here and express theta in terms of some quantities I know, just like I needed to express r in terms of quantities that I know, because really I need to get everything in terms of y. I'm going to be integrating in the y direction, and I'm not going to be integrating in the theta direction or the r direction, but r and theta both depend on y. So I need to recast this in terms of y. So cosine theta, that's going to be, here's my same angle right here. That's the opposite. Oh no, cosine is adjacent, so it's going to be a over r, and that's square root of y squared plus a squared. All right, so now I can rewrite this in terms of my components. Before I do that, the last piece of this puzzle is figuring out what dq is, because dq doesn't mean anything. I need to recast dq in terms of y, okay? That's where the linear charge density comes in. Okay, so we know that lambda is a linear charge density. That means this, this q is evenly distributed over all of this rod. That means it's q over L, right? That's the linear charge density. It's the charge per length is q divided by L. Now, in this case, since the linear charge density is q over L, dq can be written like this, right? Well, this is equal to dq over dl, but instead of dl, right, in the L direction, that would be dy. So we get this relationship between dq and dy and lambda. And so from there, you solve for dq, and you get dq equals lambda times dy. All right, sweet. I've recast dq in terms of something I can integrate over. I've got cosine theta here in terms of y and constants. R is in terms of y and constants. I'm ready to set everything up. So I get dEx equals 1 over 4 pi epsilon naught. dq, that becomes a lambda times dy over r squared. Well, that's this guy right here, so that's y squared plus a squared. Cosine theta, that's a over square root of y squared plus a squared. And now I integrate both sides. So I integrate all the electric field on this side of the equation. So this just becomes an Ex. I'm adding up all those little pieces of E to get Ex total. And that's going to be equal to, pull out my constants, I get lambda times A divided by 4 pi epsilon naught. Okay? And then what I'm left with is the integral of dy over y squared plus a squared to the 3/2 power. And the last thing I need to do is figure out what my limits of integration are. Well, I'm integrating this rod over the whole rod, and this is going from minus L over 2 to L over 2. That's half the distance of the rod, the length of the rod below the x-axis, and half the length of the rod above the x-axis. So this is minus L over 2 to L over 2. Now, there's a good chance that I'll just ask you to set this up, or I will give you a table of integrals. From there, you can go ahead and plug that into the table of integrals to get your answer. Or if you have a calculator that does calculus, you can use that too. Okay? But if you can set it up, if you can get to this point right here, that's like most of the points in the bag. Now from there, if you actually do this integration, you get E sub x equals 1 over 4 pi epsilon naught times q over a times square root of L over 2 squared plus a squared. But once again, you would consult the table of integrals and then you would plug everything in. Okay, the key points here though, this guy right here, the linear charge density, and showing how you solve for dq. That's super important. Getting the geometry over here, cosine theta, and r, recast in terms of y, which is the direction that you're going to integrate this rod. That's important too. Okay? So make sure you recast everything in the direction that you're integrating, and then set your problem. Okay? Do you guys have questions about this? You have questions about other ones? Okay. Look in the book, look at the examples, try and do the examples for a line.